In the past, we've seen how to do arithmetic with vectors. We saw how to do scalar multiplication, we saw how to add them and subtract them. What we haven't seen so far is how to multiply vectors. That's because it's something different we've never seen before. What I mean by that is, there's not just one way to multiply. There's only one way to multiply two numbers together, it's just multiplication. But for vectors, we actually have two different methods for multiplication. The first one we're going to take a look at today is called the dot product. Of course, product meaning multiplication. And then a little bit later on, we're going to take a look at something called the cross product. So there's two different methods for multiplying vectors. So let's just jump into this and see what the definition is. Here if we have two vectors, let's call them u1, u2, the vector v is v1, v2. Then by definition, u dot v is going to be, well, let's see, that would be u1, u2, dotted with v1, v2. By definition, what you do is you multiply the components together and then sum them all up. Now, a few things before we actually get into the definition. You have to put the dot there. It's the name of it. No longer does this mean multiplication. In the past, if we had two variables next to each other and we didn't have a sign in between, that was understood to be multiplication. However, if you have two vectors just next to each other, that means nothing. It's nonsensical. It doesn't make sense at all. You have to state what type of multiplication it is. So I know it sounds picky, but since there's more than one multiplication, you have to state which one it is. So you have to always put the dot in between if you're actually multiplying. Now again, very, very simple rule. Just multiply the components together and add them all up. So if this was a three-dimensional vector, we'd have u3 times v3, or u4 times so on and so forth. You just keep going ever how big that the vectors get. So let's see if I just said find u dot v if u is the vector 2, 3, and v is the vector -5, 7. So u dot v would be 2, 3, dotted with -5, 7, or 2 times -5 plus 3 times 7, -10 and 21 would be 11. Okay, so notice here when we do the dot product, we get just a number out, a scalar, so to speak. So what is this number? Well, it's kind of interesting, and we're going to be talking about this throughout the semester. When you do the dot product of two vectors, what you're kind of getting here is how much one vector points in the direction of another vector. Now, if these are unit vectors, then that's what you actually end up with. If one vector is a unit vector and you do the dot product, you get how much this vector points in the direction of that unit vector. That's exactly what you're getting. But if neither one of them are unit vectors, you kind of get how much this vector points in the direction of this vector, which is a number, times how much this vector puts in the direction of that vector. Now, your dot product can be negative. That's kind of a weird way to think about it. Like I said, that's hence the kind of. See, watch what I mean. If we had the vector, let's do u, and let's keep it as 2, 3, and the vector I. Remember, that's our standard unit vector 1, 0. Well, u dot I would be 2, 3 dotted with 1, 0. Again, after practicing a little bit, you don't need to write this step in here, 3 times 0, which is just 2. And if you think about what this looks like, if you were to do a quick sketch of your vector in standard position, that's our vector u. Remember, our vector I just points in the x direction. So the question is, how much does u go in the x direction? Well, it goes 2 steps in the x direction, right? It's easy enough to see right there. So the dot product is kind of how much one vector goes in the direction of another one. But we're going to see how we can actually put that concept to use here in a little bit. But other than that, it is just a do this to do the multiplication. Now, since it is our multiplication, we're going to need to take a look at some properties for this. Sorry about the weird cut in the video right here. The camera died there for a second. So let's talk about some properties of our dot product. Since it is multiplication, it does go by some of the rules of regular multiplication. It is commutative. u dot v is the same thing as v dot u. And that should make sense, right? If you have two vectors, 2, 3 dotted with 4, 5, well, that's 2 times 4 plus 3 times 5. You see here, the only thing changing the order here would do is change the order here, and that's just regular multiplication, which is commutative. Let's see here. What if we have, let me change this. What if we have u dot v plus w? So that kind of looks like our distributive property, right? That's another property that we have with multiplication. Well, that actually holds up the same. That would be u dot v plus u dot w. Nice and easy. So our distributive property still holds up, distributing multiplication across addition. What if we have something times 0? Now again, to do the dot product, that would have to be the 0 vector. Of course, that's just a vector full of zeros. Well, of course, that would just be the number 0 this time. What happens if you take a vector and you dot it with itself? Well, let's see. That would be something like u1, u2 dotted with u1, u2. Well, that would be u1 squared plus u2 squared. Now, notice that kind of looks like our magnitude, right? The magnitude of u is the square root of u1 squared plus u2 squared. So that's basically the magnitude just squared. So if you take a vector and you dot it with itself, you get its magnitude squared. Now this kind of makes sense with the definition I gave you of what the dot product was. It's how much one vector goes in the direction of another vector. So how much does u go in the direction of u? Well, that'd be the whole length of u, so that's the magnitude of u. And how much does this u go in the direction of that u? Again, another magnitude of u. So magnitude of u times magnitude of u would be the magnitude of u squared. All right, let's do this one. All right, let's take a look at this. If we have two vectors out there in space, and we were to draw them, let's see, there's u, there's v. We were to draw them starting at the same spot. The question is, can we figure out what the angle between these two vectors are? Well, technically there's two. There's this angle here and the one on the outside, the bigger angle. Well, anytime we're talking about the angle between two vectors, we're always talking about the smallest angle. Well, anytime we're talking about angles and stuff like this, a lot of times we're talking about triangles. So if I were to connect this side to this side would be v minus u. We'd have a triangle here. We'd have an angle and we'd have some sides. Well, kind of. We need the sides to be a length. So I'm going to draw this triangle again, exact same triangle. But now I'm going to say that these are lengths, right? That's magnitude of u. There's our theta and the magnitude of v minus u. Well, here we're trying to figure out an angle and we have three sides of a triangle, not necessarily a right triangle. Remember, that could be any triangle. So we need to go back to trig and remember how to solve a triangle. We remember back then, if we have three sides of a triangle, to figure out the angles, what you need to do is the law of cosines, which would be something like c squared is equal to a squared plus b squared minus 2ab cosine c. Now, the only things that we really need to know from here, c is the angle we're looking for, and little c is the side opposite of it. So if I'm looking for theta, that's the side opposite of it, and these are a and b. It doesn't matter which one's which. So if I plug these things into this formula with v minus u being the psi here, what we'd end up with is the magnitude of v minus u squared is equal to magnitude v squared plus magnitude u squared minus 2 magnitude v magnitude u times the cosine of theta. Ooh. What are we trying to do again? Oh yeah, remember when things get complicated, you need to always ask yourself, what are we doing? I'm trying to figure out what theta is. So I need to solve for theta here. I'm going to take a brief little side jaunt over here. We could go ahead and just solve for theta right now, but believe it or not, this left-hand side will simplify quite a bit. This is asking us to do the magnitude of v minus u squared. All right, well, what would v minus u be? Well, the vector v minus u would be v1 minus u1, comma, v2 minus u2, magnitude squared. Well, the magnitude just means square each component, and then take the square root of it, but we're squaring it, so that goes away. All right, I'm going to go ahead and distribute all this out. This is going to be v1 squared minus 2v1 u1 plus u1 squared plus v2 squared minus 2 v2 u2 plus u2 squared. You're like, I thought you said that this was going to simplify and be nice. Well, it will in a second. All right, I'm going to get the v stuff together, the stuff that just has v, so I have v1 squared plus v2 squared. If I get the u stuff together, that's u1 squared plus u2 squared. And then the pieces that have both. All right, now, this works out because of this. These two pieces end up being something nice. This is really just the magnitude of v squared. This piece here is the magnitude of u squared. And if I factor a negative 2 out of these two, I get v1 u1 plus v2 u2. All right. Now, we just saw what this is the definition of. That's our dot product. So this ends up being magnitude v squared plus magnitude u squared minus 2 u dot v, or v dot u. I don't care where you write that. All right, so this thing simplifies to this. You're like, well, that doesn't look any more simple, but watch what happens to our equation if we put that in. It ends up being the magnitude of v squared plus magnitude u squared minus 2 u dot v, magnitude v squared, magnitude u squared, minus 2 magnitude v, magnitude u, cosine of the angle. All right, messy, but since these are on both sides, they're going to reduce, and we get negative 2 u dot v is equal to negative 2 magnitude, it doesn't matter, u magnitude v times the cosine of our angle. Or solving real quick, you can see that the cosine of the angle is u dot v over the magnitude of u, magnitude of v. All right, so this is generally where we leave our formula. We generally don't say that's the arc cosine, even though that's what you're going to have to do. Now, a quick check. If we have two vectors, we said that the angle between them is always the smallest. Well, if you think about it, what's the biggest the smallest angle can be? Kind of a weird sentence. But if you think about this opening up, the biggest it can be is 180 degrees, right? Or pi. So where is the arc cosine defined? Well, if you remember, the arc cosine, I'll take calculus, is defined in the first and second quadrant. So this will give us an answer from 0 to 180 degrees. So we don't have to worry about any reference angles occurring when we use this formula. All right, so it is just a formula. By the way, another way to look at this formula, we're really just, the cosine angle is the dot product of both unit vectors, u and v. Right, because if you take a vector and divide by its magnitude, you get the unit vectors. But most of the time you see the formula written like this. All right, a couple of results that we get from this. I'm just going to move this over here. By the way, you need to know that formula, memorize it. Very, very helpful. What if theta is 90 degrees, or pi over 2? Well, if I plug that into my formula, that's the cosine of 90 degrees is equal to u dot v over magnitude u, magnitude v. Well, the cosine of 90 is 0, so that's u dot v, magnitude u, magnitude v. Well, I can clear these fractions because remember the magnitudes are just numbers, so that's just a number, which implies that u dot v is equal to 0. All right, this is a pretty important result because it says, we can read this in both directions. It says if u dot v is equal to 0, that means that the angle between them has to be 90 degrees, and if the angle between them is 90 degrees, that the dot product is equal to 0. Now this is going to be a new definition for us. If u dot v is equal to 0, then u and v are something called orthogonal. Now, since the angle between them is 90 degrees, most of the time we use the word perpendicular. We're going to have three words that almost mean exactly the same thing in this course. Perpendicular, orthogonal, and normal. So these three words, perpendicular, orthogonal, and normal, all mean really, really close to the same thing, and are almost interchangeable, and sometimes they are. Perpendicular means that two things meet at 90 degrees. Orthogonal means that their dot product is 0. Does that mean that they meet at 90 degrees? Yes and no, depending on a little bit later on. These things don't have to be vectors, they can be other things, so it gets a little bit more complicated there. And normal, again, means at 90 degrees, but normal we're talking about to a surface. So if you have some three-dimensional surface out there, who knows, some three-dimensional thing, normal means that it meets that at 90 degrees. So again, not quite the same thing as perpendicular. Perpendicular is generally a two-dimensional concept. Orthogonal is really talking about the dot product. It can also mean perpendicular. And normal, we're almost always talking about upper dimensions and what that means. All right, we still got a lot more to talk about the dot product, but I think that's going to finish this one up.